Hi guys, let's take a look at section P.4, and this section is on trigonometry. And we're just going to do a quick overview of what I would consider the most important topics in trigonometry. So you probably took pre-calculus or trig class somewhere previously, and you spent a lot of time doing a lot of things with trigonometry. There's a lot of stuff to remember, but I'm going to just try to hit the highlights of the things that you need to be sure you remember that we're going to use most often in this class. So in the guided notes, you've got a list of a lot of the common identities, trig identities. Now we're not going to use all of these in this class, so the ones that I think are probably most important, that will come up most often, that you'll want to be familiar with, are the Pythagorean identities. So these three right here, sine squared theta plus cosine squared theta equals 1. That's a really, really common one. The even odd identities, you don't have to memorize these or remember them, but you probably would help you down the line to remember which functions are even and which ones are odd, especially for sine and cosine. So remember in the last lesson we talked about the definition of an even function. So to be an even function, just in general, the definition is that f of negative x was equal to f of x. So with that as the definition of an even function, take a look at this list and can you tell which ones would be even? So which ones fit this definition according to this list of identities? You can see cosine. Cosine would be an even function, and that's important because that means it's going to have symmetry over the y-axis. And then its reciprocal, secant, of course, is also even. And then really the rest of them are odd. So remember the definition of an odd function is that f of negative x was equal to negative f of x. So you can see that sine is an odd function because it fits that definition. So is its reciprocal cosecant. And so that means that sine has symmetry, or what kind of symmetry? It's odd, so it would have origin symmetry. And then tangent and cotangent are also odd. The main two from this list that we're going to see most often are sine and cosine. If you can remember which one's even and which one's odd, that'll help you out. Sum and difference, we're not going to do a whole lot. The power reducing and double angle, we're probably not going to do a whole lot in this class. Law of cosines, I don't think we'll use very often. The reciprocal identities and the quotient identities, however, are very important. Those would come up a lot. So you got to remember what the reciprocal functions are for which trig identity. So cosecant, of course, is the reciprocal of sine. Secant is the reciprocal of cosine. Cotangent is the reciprocal of tangent. And then the quotient identities, remember that tangent theta is always equal to sine theta over cosine theta. Cotangent theta, of course, is the reciprocal of tangent, so that means we would flip it and get cosine theta over sine theta. So the ones with the stars there are probably the ones that are most common that we're going to see in this class. So let's talk about angle measurements. In your last math classes, you would have learned to look at the unit circle. So remember what the unit circle is. And you'd look at the angles on the unit circle and according to the ones that are most common, the special angles. And you would look at them in both degrees and radians. I'm going to tell you right now, in calculus, we never, ever, ever use degrees. We are always going to use radians all the time. So the more comfortable you are with radians, the better things are going to go for you. If you want to know the degrees, or if you remember the degrees and they kind of help you to remember what the radian measures are that go with each one, that's fine, no problem. But when we look at a problem, it's always going to be radian measure. So let's just go through the main ones here. So 0, of course, is 0 in radian measure. 30 degrees, remember that's in the first quadrant, that's pi over 6. 45 degrees in the first quadrant is pi over 4. They both have a 4 in it, that's how I remember it. And then 60 degrees is at the top of the first quadrant there, that's pi over 3. And then 90 degrees is on the y-axis, so remember that's at pi over 2. And then beyond that, remember each quadrant in the unit circle has a pi over 6, a pi over 4, and a pi over 3 value. But the next quadrant angle that you would come to is 180 degrees. So remember on your unit circle, if this is 0, this is pi over 2 up here, pi would be over here. That's 180 degrees. And then down here at 270, that would be equivalent to 3 pi over 2. And then if you go back to the 0, remember that's back to 2 pi. So we need to know the sine and the cosine values for each of those angles, and I think the rest you can figure out as long as you know the reciprocal and the quotient identities. All I have memorized are sine and cosine, and the rest I figure out as I need them. I put these in, you know what, I'm actually going to make a change to the notes here. I'm going to make this cosine theta, and I'm going to put sine theta. And the reason I'm doing that is because, there it is, because the cosine and sine, remember, you can think of as like an x and a y coordinate. Cosine's like your x-coordinate, sine's like your y-coordinate. So I'm going to put them in order so they follow that pattern. So at 0 degrees, so that's, or 0 radians, I should say, that's, you know, where you start off on your unit circle. Remember that the x value, the cosine value there is 1, and the sine value is 0. At pi over 6 radians, that would be where cosine is square root of 3 over 2, and sine is 1/2. 45 degrees or pi over 4 radians, that's where they're the same. Remember, that's the easiest one to remember, I think, because cosine and sine are the same, and they're both the square root of 2 over 2. 60 degrees, that would be where cosine and sine, they reverse, so that would be a cosine value of 1/2 and a sine value of square root of 3 over 2. And then at the top at 90 degrees, that's the top of your circle up here, you're on the y-axis, so your cosine is 0 and your sine is 1. At pi, you're over here on the negative side of the x-axis, so you go to -1 for the cosine and 0 for the y, or the sine value. And then at the bottom at 3 pi over 2, you're at 0 for cosine and -1 for sine. And then it starts over at 1, 0. You do need to know those. You do need to have them memorized. They're going to come up quite a bit. I have some little tricks I can show you either in class or in the office if you want some help remembering these, but you got to be familiar with them. So let's just do a few examples here. Sine of negative pi over 3. Now, negative pi over 3, that's a negative angle, so it's not on our original, you know, one trip around the unit circle. Negative angles, remember, that means you go backwards on the circle. So if we rotate counterclockwise when we go around the circle, so for a negative angle, we're going to rotate clockwise. So what that means is starting at 0, I'm going to go backwards pi over 3 radians, which puts me in quadrant 4. So in the fourth quadrant, think about sine. Sine is the y-coordinate, so with the value in the fourth quadrant for the y-coordinate, would that be positive or negative? And that would be negative. So we know it's going to be negative something. Now what is it going to be? Well, it's going to be the same thing as the value at pi over 3. So if I have the sine of pi over 3 memorized, which I do, that's square root of 3 over 2, I know that the sine of negative pi over 3 in the fourth quadrant is going to be negative square root of 3 over 2. Secant of 60 degrees, now I just got done saying we're not going to have anything in degrees, so let's pretend this was radians. Let's just go ahead and pretend it asked for secant of 60 degrees, which of course is pi over 3 again. All right, so that's the regular angle in the first quadrant. Actually, it would be up here, right? Pi over 3. And so to get secant, I don't know secant, but I know cosine, right? And secant is the reciprocal of cosine. That's what I have memorized. So the cosine at pi over 3 would be 1/2. So to get the secant, I'm going to take the reciprocal of it, because remember, secant and cosine are reciprocals. So the reciprocal of 1/2 would be 2 over 1, or just 2. Cosine of 5 pi over 6, so let's think about what quadrant that would put us in. 5 pi over 6, 5/6 of a pi. So remember your circle, you start out here at 0, pi would be over here. So 5/6 of a pi would be less than a full pi. So that would be the angle that's in quadrant 2. So that's your pi over 6 value that's in the second quadrant, 5 pi over 6, right there. Remember I said each quadrant gets a pi over 6, a pi over 4, and a pi over 3 value. There's a little counting trick. I can show you this in class tomorrow that I kind of use, especially with the pi over 6s. That kind of helps me remember them. But the other way to think about it is just think 5/6 is less than a whole pi, because this would be 1 pi. So it has to be in quadrant 2. So, all right, think about cosine in quadrant 2 then. Cosine is the x-coordinate, so in quadrant 2, would that be negative or positive? And cosine would be negative because the x's are negative in quadrant 2. So it's going to have the same value as the cosine of pi over 6, which is what I have memorized. It's just going to be negative because it's in the second quadrant. So pi over 6, we'll look at our chart here. Cosine value there is square root of 3 over 2. So the value there is going to be negative square root of 3 over 2. So this is the next sort of most common thing we're going to do with these trig functions, is we're going to need to solve some basic trigonometric equations. We're not going to get really complicated with these. Some of these can get really, really complicated, but we're going to keep them pretty simple. But every so often they're going to come up in this course. We're going to be asked to solve an equation in some capacity related to calculus. And they usually will restrict you to the interval 0 to 2 pi, so just one trip around the unit circle. And we need to know where those angles occur. So that goes back to knowing the values in this chart and knowing which quadrants we would be talking about for a given angle. So let's take a look at the first one. Sine theta equals negative square root of 3 over 2. First thing I would do is identify the quadrants the solution to this would be in. Sine is negative, so think about if sine is the y value, which quadrants would sine be negative in? And you should be thinking y's are negative in the third and the fourth quadrants. So that means my solutions here are going to be in quadrant 3 and quadrant 4. We're going to have two solutions in that interval 0 to 2 pi. Then I need to know, okay, what reference angle from this chart does sine equal square root of 3 over 2? All right, and again, you need to get comfortable with these numbers. You need to remember these numbers. You're not going to be able to use this on a test or anything. But you need to know, okay, sine is equal to square root of 3 over 2 at which of those special angles? And for now, we'll look at the chart and see that it's right there at the pi over 3 angle. So what we want is the pi over 3 angle, but we want the one that corresponds to quadrants 3 and quadrants 4. So this was sort of that counting trick I mentioned a second ago. This is how I figure out the values for the different radians in each quadrant. And I think about it this way. So pi over 3 we know is in the first quadrant, right? So pi over 3, pi over 6, pi over 4, 1 pi over 3. That's in the first quadrant. Count until you get to the next pi over 3 value that does not reduce, and that will be the angle that goes in the next quadrant. So if I'm at 1 pi over 3 in the first quadrant, if I count, the next one would be 2 pi over 3. 2 pi over 3 doesn't reduce, so that would be the one in quadrant 2. Well, I got to keep going because I want the ones in quadrant 3 and quadrant 4, so let me keep going. So quadrant 3, would it be 3 pi over 3? So I'm just counting. 1, 2, the next one would be 3 pi over 3. Well, that's not it because that reduces, right? 3 pi over 3 would actually be the same as pi. Okay, then would it be 4 pi over 3? Yes, because 4 pi over 3 doesn't reduce. So 4 pi over 3 is the pi over 3 angle in quadrant 3. Okay, keep going because we need the one for quadrant 4 also. So count again. If I'm at 4 pi over 3, go to the next one, it would be 5 pi over 3, and that doesn't reduce. So that's the one that's in quadrant 4, okay? So my solution here, theta, would be equal to 4 pi over 3 and 5 pi over 3. A lot of times these will have more than one solution, and there you go. Let's look at the next one. This time we've got cosine squared x equals 1/4. First thing we need to do is get rid of that squared, right? So think if I just had x squared equals a number, to solve it, we would take the square root of both sides. The thing to remember when you take a square root is the plus minus. So what we end up with is cosine x equals plus minus the square root of 1/4. Well, square root of 1 is 1, square root of 4 is 2, so that's going to be 1/2. So we're looking for all the angles between 0 to 2 pi on the unit circle where cosine equals positive 1/2 and negative 1/2. Okay, well, let's think about this. Where does cosine equal 1/2? Just in the first quadrant. That comes from my table again. Cosine would equal 1/2 at pi over 3 radians, right there. Again, it's pi over 3. So that means I want the pi over 3 values that are both positive and negative, okay? Or that produce both positive and negative cosines is what I should say. Well, we just counted them, so I'm not going to go through it again. But this time we're going to take all 4 solutions because cosine would be positive in quadrant 1 and quadrant 4, right? Because that's your x values. Cosine's like your x coordinate. Cosine would be negative in quadrant 2 and quadrant 3. So our solution this time is going to contain all 4 pi over 3 values. Pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. And so this time we have all 4 solutions. Okay, let's try the next one. We've got sine squared x minus sine x equals 0. We have more than one sign, so to solve this we're going to have to use factoring. Okay, remember zero product property and factoring. Anytime you have something that's squared where you can't just take a square root like something squared equals a number, but we have more than one sign term, we have something squared, this is something we have to factor. So think about it just like you'd factor if you had x squared minus x equals 0. To solve that, you would factor an x out, and you'd have x times x minus 1. It's the same idea. We're going to factor a sine out, and so that leaves me with sine x minus 1 equals 0. And then we're going to use the zero product property, so we're going to set sine x equal to 0, and we're going to set sine x minus 1 equal to 0. Over here, where does sine x equal 1 from this equation, and then where does sine equal 0? Well, on your unit circle, think about where sine would equal 0. Of course, it would equal 0 at the original sine value, or at the original angle, 0, right? And then again at pi is the next location. So for that part of the solution, my solutions are going to be 0 and pi. Where does sine equal 1? Well, that's at the top of the unit circle, right? That's the angle on the y-axis at the top, so that would be pi over 2. So I have 3 solutions this time, 0 and pi from this first part of the equation, and then pi over 2. I did not include 2 pi. If we go back around the circle again, we'd get the same location as 0 because they left it out in the interval notation up here. It would be fine if you included it, but it's the same thing as 0, so we've already accounted for it. Let's take a look at letter D. Again, we're going to have to factor this. So this time we have 3 terms. We have a sine squared, a sine, and a 1. We're going to treat this like a quadratic equation where we would factor it, factoring a trinomial, right? So we're going to factor this way into 2 binomials. First 2 terms need to multiply to 2 sine squared x, so we're going to have 2 sine x and sine x minus, or just sine x. And then the last terms need to multiply to 1. Well, it has to be 1 and 1, that's the only option. And it has to multiply to a negative 1, which means the signs have to be opposite, but it has to get me to a positive sign on the inside. So that means the outer term in this case, which would be 2 sine x, would have to be positive. The inner term, which would be just sine x, has to be negative. So there's my 2 factors. We're going to use the zero product property again. We're going to set those equal to 0. So we have 2 sort of mini equations to solve. All right, so add 1 and divide by 2. We're looking where sine x equals 1/2 and where sine x equals negative 1. So sine x equals 1/2. So think about in the first quadrant, where would the sine value equal 1/2? And that would be at your pi over 6 location. Where is sine positive in which quadrants? So that would be in quadrant 1 and quadrant 2. So we want the pi over 6 values in quadrants 1 and quadrants 2. Well, in quadrant 1, of course, it's just pi over 6. In quadrant 2, so this is that sort of counting trick I was talking about a little bit earlier. If pi over 6 is in the first quadrant, the next quadrant would be a pi over 6 value. If you count, so this is 1 pi over 6, would the next one be 2 pi over 6? No, because it reduces. Would it be 3 pi over 6? No, because it reduces. Would it be 4 pi over 6? No, because it reduces, so the next one would have to be 5 pi over 6, because that's the next one you get to that does not reduce. Let me write that down here. And then other part of the solution, where does sine x equal negative 1? Well, that would be at the bottom of the y-axis, so that would be at 3 pi over 2. So we have 3 solutions to this equation. All right, so let's look at example E there. They're asking us where does tangent x equal square root of 3. A little more complicated here because it's not just a sine or a cosine. So what I always do when I have a tangent or a cotangent or something like that, what I think about is the quotient identity. So if you remember that tangent x is equal to the sine over the cosine value, right? So that's our quotient identity. That was back here in the notes, but that's one you should know. Tangent's equal to sine over cosine. And so if I remember that, what I'm looking for is the location where the numerator will have a square root of 3 in it. And square root of 3 really is the same as square root of 3 over 1, right? So the numerator needs to have a square root of 3 something, and the denominator needs to have a 1 something. Well, we're limited to unit circle values here. We're not using a calculator to solve these. So these are all angles that should come from our chart. So think about what we're looking for. We're looking for an angle where the sine, the numerator, would have to be square root of 3 over 2. And the cosine, the denominator, would have to be 1/2. Remember, square root of 3 over 2 and 1/2 always go together. So, you know, this is really equivalent to the square root of 3 over 2 over the 1/2. Really, it's a simplified version of this location where this angle occurs, right? Because those 2's wouldn't stay, they'd go away. It'd reduce and just leave me with this. So kind of thinking backwards, if I have a location where tangent equals square root of 3, that means the numerator sine has to be square root of 3 over 2. So where does sine equal square root of 3 over 2? First of all, let's talk about the quadrants we're in. it's a positive tangent value. That means the sine and cosine have to be the same values, either both negative or both positive. So we know we're working in quadrant 1 because they would both be positive there. And then in the other quadrant, where's the other quadrant? Think about where sine and cosine are the same signs, SIGN signs. And that would be in the third quadrant, right? A negative divided by a negative would result in a positive tangent value. So I'm looking for the angles in quadrants 1 and quadrant 3 that correspond to this location. Well, where does sine equal square root of 3 over 2? That would be at pi over 3, right? Square root of 3 over 2 for your sine value right there. That would be at pi over 3. And then we want the one in the third quadrant. So remember earlier we did that and we said that was 4 pi over 3. So those are my two solutions, pi over 3 and 4 pi over 3. Had they asked me for a negative square root of 3, then it would have been the opposite quadrants, quadrants 2 and quadrants 4, and we would have found the pi over 3 values in those quadrants. Last example, so we have cosine of 2 theta now. So notice we have a double angle. I said earlier we weren't going to do much with the double angle formulas, but this is a situation where it might be helpful if we can get rid of that double angle, that 2 theta, by replacing it with one of these double angle formulas. Now, cosine of 2 theta, there's actually 3 equivalent versions of that formula. It comes from the Pythagorean identity. So think about which of these 3 versions of cosine of 2 theta would be most helpful considering the rest of this equation. The rest of the equation has a sign in it, right? So it would be easier, I'm thinking, if we can get everything in terms of signs. So look at your equations. One of these will do that for us. And you see that's the second equation, 1 minus 2 sine squared theta. So I'm going to replace cosine 2 theta with 1 minus 2 sine squared theta. Okay, so make sure you're looking at this problem. Equals 2 minus 3 sine theta. So we're going to kind of treat this like the others where we want to get everything to one side and we want to factor it because we've got that sine squared term in there. Because of the negative 2 sine squared theta, I'm going to move everything to the right side because that'll make that 2 sine squared theta positive. So I'm going to add 2 sine squared theta to both sides. At the same time, why don't we go ahead and subtract the 1. So that leaves me with 0 on this side equals positive 2 sine squared theta minus 3 sine theta. And then I have a 2 and a negative 1 now, so that gives me a positive 1 at the end. All right. So now we have a quadratic that needs to factor. Essentially, it's the form of a quadratic. So the first 2 terms have to multiply to 2 sine squared theta. So we have 2 sine theta and sine theta. We have to have a 1 at the end, so it's got to be a 1 and a 1. It's got to multiply to a positive 1, but add to a negative middle term, so that means both of these have to be negative. If you FOIL that out, you'll see that that gives us the negative 3 sine theta in the middle. So now we're going to set both of these little mini equations equal to 0. And we're going to solve. So once again, we have where does sine theta equal 1/2? I think we had that one in an earlier problem. And then where does sine theta equal positive 1? So sine theta we said was equal to 1/2. Remember that would be in quadrants 1 and 2 because it's a positive sine value. That's like your y coordinate. And it would be at pi over 6 in the first quadrant, and then the other value, the pi over 6 value in quadrant 2, we said was 5 pi over 6. So there's part of our solutions. And then where does sine theta equal 1? That's at the top of the circle at the pi over 2 location. So we have 3 solutions there. All right. Last little thing, and I'm not going to spend much time on this, but you do need to be somewhat familiar with the graphs of the trig functions, particularly sine and cosine. Those are the ones that will probably come up most often. Maybe occasionally we'll have a tangent that'll come up. The reciprocals are not quite as common, so don't stress too much about those if you don't remember them, but I do want you to remember the sine and cosine graphs, the basic shapes and the symmetry. So the first one is the graph of our sine curve. You'll notice that it's got origin symmetry. Remember, this keeps going forever, right, in both directions. So it's got origin symmetry, which makes sense because a few minutes ago we said sine was an odd function. Sine, remember, goes through the origin, 0, 0, that's that coordinate, and then it goes up from there. All right, so one full cycle would be from 0 to 2 pi. For the cosine curve, notice this has y-axis symmetry. If you extend it, it's a little easier to see it, but the left and the right side, they're symmetric over the y-axis. maybe not the way I drew it there, but hopefully you get the idea. Cosine, remember it starts off at the top at 0, 1, because that's the value at 0 radians. And then 1 full cycle, gets back up there, would be at 2 pi again. So 2 pi is the cycle for that one. Tangent, just a couple things to remember. Tangent's the quotient identity for sine over cosine. So wherever cosine equals 0, that's where you're going to have your asymptotes, right? So where does cosine equals 0? That would be at pi over 2 is the first location on there. 3 pi over 2, 5 pi over 2, negative pi over 2. Those are going to be your locations of your asymptotes. And then remember, tangent goes up on the right, down on the left, and repeats every pi radians.